this video, I'm going to be going over some practice multiple choice questions about parametrics. So the worksheet is in the description, so work through it yourself, and then if you get stuck, you can watch this video. So the first question gives us a velocity vector, and it wants us to find the acceleration vector. So when we have a vector represented like this, the first term, here it's t squared, is the x component of velocity, and the second term is the y component, because we can represent vectors as two components, an x component and a y component. So earlier in the year when we studied motion, it was always one-dimensional. It was either always on the x-axis or always on the y-axis. So one of these components would be 0, but now we have both components. So it's a little more complicated. So to find the acceleration vector, we just differentiate the components separately. So the x component of acceleration will be the derivative of t squared, which is just 2t. And then the y component of acceleration will be the derivative of 5t. So the acceleration vector is 2t, comma 5, and then it asks for the vector when t is 3, so that's just 6, comma 5. Question 2 is an arc length problem. So basically we just use this formula. A bounds of integration are 0 and pi. And then we need to find dx dt and dy dt. So we do that, and then you need to square them, and after that you just plug them into the formula to get this. Question number 3 gives us a regular equation in terms of y and x, but then it wants us to find dy dt. So the first step we need to do is differentiate this equation with respect to time. And so we get this. And then we can factor out this dx dt to get dy dt equals dx dt times 2x minus 1. Now, the problem also gives us the speed. Now, the speed is the magnitude of this velocity vector. And so, if we want to find the magnitude of the vector, we have to use the Pythagorean theorem. So, see, the velocity squared is going to be equal to the x component of velocity squared plus the y component of velocity squared. So we get this equation, and from there we can replace dy dt with this expression that we found earlier, and replace v, the velocity, with the value it gives us of 2 square root 10. And then we can factor out a dx dt squared to get this. And then from now, all we have to do is plug in x equals 2, because that's the value, the position it gives us in the problem. And we find that dx dt is equal to 2. And once we have dx dt, all we have to do is go back to this first equation to solve for dy dt. So in problem 4, it just asks us for the slope of the tangent line. So really all we have to do is find the dx dt and dy dt separately, and then we plug in t equals 13, and then just use the formula for the tangent line, dy dt over dx dt, to find the answer. Question number 5 is again just the slope of the tangent line. So we just find dx dt and dy dt, and then divide dy dt by dx dt. And to find the value of t, it gives us that the y value is 8. So all we have to do is solve for t. And we get that t equals 2. So we just plug that in. And we find that the derivative is 12 over 0. Now remember that if the bottom is 0, then we have a vertical tangent line. So the equation of the tangent line will just be x equals -3. Now, question number 6 asks us for the speed of the particle. So the first thing we do is find the x and y components of the velocity vector. And then once we do that, we just use the Pythagorean theorem to find the magnitude of the overall velocity. And question number 7 is another slope of the tangent line problem. This one's pretty easy. Again, you just differentiate separately to find dx dt and dy dt, and then use dy dt over dx dt to find the slope of the tangent line. Problem number 8 is another acceleration vector problem. So it gives us the position vector as the parametric equations. So we differentiate once to get the velocity equations, and then twice to get the acceleration equations. And then after that, we just plug in t equals 1 to find the x and y components of the acceleration. So a vector is 6, 24. For problem number 9, it's another Oakland problem. So again, we just use the formula. We have dx dt is t squared, and dy dt is just t. So then you square them and plug them in to the formula, and it balances 0 to 1. Problem number 10 is a vector problem. So again, we have the x component of the vector and the y component of the vector. So all we have to do is just differentiate them separately. So here we're looking for the second derivative. So we do that, and then those are just the x and y components of a new vector.